discussion on this. So what we like to do, we like to compute this integral. And in order to compute this integral, we need to keep in view that fx of x is 1 when x is between, what do you call, 0 to 1. So hence, this integrand would be 1 if a minus y is going to be between 0 and 1 actually. So, what would we like to do? So here are the key things that we have to take in consideration. So consider one thing, that y is have what do you call a kind of a universal inequality or universal constraint, that it is always between 0 to 1 actually. Okay. Secondly, fx of a minus y is going to be equal to 1 if and only if a minus y is going to be between 0 to 1 actually. So this is true. And this means that a should be between y and 1 plus y. Okay? But for y, I know that this is bigger than or equal to 0, and y can take the biggest value 1, so the a should be less than or equal to what you call 1 plus 1 into 2. That is, that a must be between 0 to 2. So hence, what we are saying, so we are saying that if your a is between 0 to 2, and your y is going to be between 0 to 1, then your a minus y is going to be between 0 to 1. And if this is the case, then fx of a minus y must be, what do you call, 1 actually. Okay? So if your a is between 0 to 2 and your y is between 0 to 1, then your fx of a minus y must be 1 actually, because then a minus y would be between 0 to 1, and we will be in position to solve this integral actually. Now you can immediately realize actually that it is pretty much wise to consider the basic two cases actually, when a is between say 0 to 1 and obviously y is between 0 to 1 actually. So if a is between 0 to 1, so I am in this interval, okay, so I am okay with it, and y is between 0 to 1, then fx of a minus y would be, what do you call, 1. But the question is, okay, fx of a minus y would be equal to 1, because the a minus y would be between 0 to 1 if a is between 0 to 1 and y is between 0 to 1 actually. The question is, what would be the limits on the y if y is between 0 to 1 and a is between 0 to 1 and this constraint is also satisfied. Now if you think about this constraint, then I can say, if this part of the constraint, which is a minus y bigger than or equal to 0, what you can deduce from here is that this shows that y is less than or equal to a. But y is also bigger than or equal to a. So case 1, if a is between 0 to 1, then y, since it is between 0 to 1 and a is between 0 to 1, the y would be between 0 to a actually. So I hope it is making sense to you. How did I deduce? That since a minus y is greater than or equal to 0, so the a would be greater than or equal to y and y is greater than or equal to 0, so this means that y must be between 0 and a. In other words, that y would be less than or equal to a, but we know about the y from this universal constraint that it is greater than or equal to a, so you deduce that you're going to have this. And hence, if this is true, then this integral fx plus y of a will become an integral from 0 to a, and fx of a minus y will become 1 and dy, and hence the integral will become a actually. So that's the first case. So in this interval, if you now choose A to be something between 1 to 2, okay, the question is again, what would be the interval, where would be the y? So one thing that I know about the y is that it is always between 0 to 1. It can't go beyond it, because in this integral, it can't go beyond this actually. But now, if you take this other side of the constraint actually, and you say that your A is between A minus y is less than or equal to 1, okay? So as from this constraint, A minus y is less than or equal to 1, okay? So you can say that A minus 1 would be less than or equal to y. And what would be the worst value or the greatest value that y can take? So from this constraint, you can say that this takes the value y actually. What the value 1 actually. So you have to, readily play with three inequalities. These three inequalities, and you can have these two conclusions actually. And if this is the case, then fx plus y of A would be an integral of 1 with respect to y, because fx of A minus y will become 1, where the y is going to be in worst case scenario between A minus 1 to 1. Because if A is between 0 to 1 to 2, then y can stay between 0 to 1 if and only if y stays between 0 to minus A minus 1 to 1 actually. So this is what that you can deduce easily. And if you compute this, okay, if you compute this integral, so what you're going to get is really 2 minus A. And hence, the final conclusion you get is that fx plus y of A is going to be equal to A if A is between 0 to 1, and it's going to be 2 minus A if A is between 1 and 2 actually. So this is what that you're going to get. So this is really the PDF of the sum of the two uniformly distributed random variables. And if you really plot the curve of this actually, so if this is the interval, so this is A-axis and this is really fx, this is A-axis and this is fx plus y-axis, okay, so then you're going to say that in the interval 0 to 1, okay, in the interval 0 to 1, you have the equation y equal to A, which is going to be a some kind of, what do you call, such kind of a line actually. And from between 1 to 2, okay, what would be between the fx of y plus 1 to 2. So if you plot 2 minus A, so you're going to get what you call something like this. So looking at the shape of the curve, we say that if x and y are uniformly distributed, their sum has a triangle distribution actually. So this is called the triangular distribution. Okay, so you can also call triangular distribution. This is triangular distribution actually, which is not necessarily uniform. Okay, so hence, if x and y are two uniform distribution, their sum is not necessarily uniform, but it has a triangular distribution actually. Okay. So let's now move to something else. let's move to, for example, the sum of two normally distributed random variables. So let's talk about sum of two normally distributed random variables. So next is sum of two normally distributed random variables. Okay, so in previous calculation, what we saw that if you have two uniformly distributed random variables, their sum is not necessarily uniformly distributed actually. Okay, so it has what we call this triangular distribution. So it has a different distribution actually. Let's see what happens in this case. So let's imagine that let's imagine, so we will start with two. So actually what we would like to show is that basically, so the claim here is this. So the claim here is this. Imagine I have x that is normally distributed with mean mu x plus variance sigma square x, and y is normally distributed with mean mu y and standard variance sigma square, what do you call y, then x plus y has a distribution, then x plus y is normally distributed with mu x plus mu y and sigma square x plus sigma square y actually, and obviously you have to assume that these are two normally distributed independent random variable actually. Independent random variable. So we have to kind of encounter this independence a lot actually. So if x is normally distributed with these parameters and y is normally distributed with these parameters, then x plus y is normally distributed with these parameters. So this is what that I would like to prove actually. So what I'm going to do, I'm not going to prove this directly, but I'm going to prove another statement from which I will deduce this actually. Okay, so I'll prove something else from which I'll deduce this. Okay, so you don't have to work too much hard. Sometimes work cleverly, and you can get your outcomes actually. So here's the thing. So we will first show that if x is normally distributed with, say, mean 0 and variance, what do you call, sigma square, okay, and y is normally distributed with mean 0 and 1, then x plus y is normally distributed with mean 0 and 1 plus sigma square actually. Okay, so we will prove this, and from this we will deduce this generic result actually. Okay, generic result. Okay, so how to do it? So in order to do it, what we would like to do, we will like to use our interesting equation, our formula. What is the formula? The formula that we will like to use is this actually. That so we will use this generic formula that the sum of the PDF of the sum of two independent random variables evaluated at A is the convolution of the PDF. The PDF of two the sum of if you have two independent random variables, okay, then the PDF of the sum is basically equal to the convolution of the PDF of x with the PDF of y actually. So it goes like this, so minus infinity to infinity, fx of a minus y, okay, times fy of y actually. Okay, so this is what that I would like to do actually. Okay, and dy. This is what the topic fx of a minus y, fy of y, and dy. So let's compute what would be fx of x, fx of a minus y and fy of y, then compute their product, and then integrate the thing from minus infinity to infinity with respect to dy. By the way, what would be the PDF of the normally distributed random variable with mean 0 and variance of mu square actually? So fx of x is going to be 1 over square root of 2 pi sigma, okay, and e to the minus x minus mu, so mu is 0, x square over 2 sigma square. So this is what is going to be the PDF of x actually. And what would be the PDF of y? So the fy of y is going to be e, so it's going to be simply 1 over square root of 2 pi e to the minus y square over 2 actually. So this is what it is going to be. So what would be this product if you compute it explicitly? So fx of a minus y times fy of y is going to be what? So in this, instead of x, replace x minus y, so it's going to be 1 over 2 pi sigma e to the minus a minus y square over 2 sigma square times 1 over 2 pi e to the minus y square over 2. So this is what it is going to be. And if you simplify this, what you're going to get 1 over 2 pi sigma and the sum of these two powers actually. So let's see what you get actually. So this is what that you're going to get. Oh yes. So if you simplify this a little bit further, so you're going to get 1 over 2 pi sigma and e to the minus. If you simplify this, you're going to get a square plus y square minus 2ay. Okay, so this would be, the power would be added, and then if you take for example LCM, so the LCM will become, what do you call, 2 sigma square times 2 2 sigma square times minus sigma square y square. So this is what that you can get actually. Okay, this is what that you're gonna get. And now, so you have to make simplifications actually. And now, if you have 1 over 2 pi sigma, so what more simplifications you can make actually, you can make this simplification that if you, for example, take away this, so I can keep this because all 3 other terms involve what you call y. Okay, so all 3 other terms they involve y, while this term is independent of y. So if I wish, I can separate it actually. So it's going to be e to the minus a square over 2 sigma square. This is what that you're going to get, and then exponential of, let me write it exponential rather than this so that I can write it things more conveniently, times c, okay, c e to the minus y minus 2y a over 1 plus sigma square. Okay, this is what that you can get actually, where the c is 1 plus sigma square over 2 sigma square actually. So it's going to be 1 plus sigma square over 2 sigma square, okay, where c is 1 plus sigma square over 2 sigma square. Okay, this is what the c is. And no, so this is not really, okay, so doing a silly mistake. So this is c times of r.v, the minus c times of y square minus 2y a over 1 plus sigma square. This is what that you're going to get, where c is this. And this makes sense actually. So if you keep this term here, so what is going to remain is e to the minus y square and minus sigma square actually. So the minus y square and minus sigma square, when you combine them, is going to be 1 plus sigma square divided by sigma square. So the 1 plus sigma square divided by 2 sigma square, I gave it a name c actually. And in other words, if you simplify this, you're going to get the same expression. Okay, so I'm leaving this simplification for you actually. And what I would like to do next, I would like to calculate this integral actually. So we calculated this. So we calculated this product, and now integrate both sides from minus infinity to infinity. This fx of a minus y and fy of y, and what do you call dy, and then integral of, so this would be outside, e to the minus a square over 2 sigma square, okay, over is 2 pi sigma times the integral of minus infinity to infinity exponential of whatever is written here dy. This is what that's going to get actually. Now if you see, this is like a quadratic equation in y actually. So we know about the normally distributed random variables that we will, so the integral becomes much more easier since we know about e. So if you have e to the minus x square upon 2, that goes from minus infinity to infinity. So I think this is equal to the square root of 2 pi. Okay, this is equal to the square root of 2 pi. So if I can convert this integral or the integral of this exponential in such a form, completing a square form, then I know that its integral is equal to what you call square root of 2 pi. But in order to write this exponential in such a form, I need to do the completing square actually. So let's do the completing square. So it's a bit messy work, it's a bit calculation, but it's not something that is hard to do actually. So y square minus 2a over 1 plus sigma square times y, so what should be added? So we should add a over 1 plus sigma square so what you're gonna get. So you're gonna have yes, so you have to do what? So you have to a square over, or maybe a over 1 plus sigma square chi square minus a over 1 plus sigma square chi square. So this is what that you're going to get. So if you take this, then you can write this as y minus a over 1 plus sigma square and everything square actually minus a square over 1 plus sigma square. This is what that you're going to get. 1 plus sigma square chi square. Okay? So this expression is equal to this. And now multiply the minus c with these two expressions actually and see what you get. So when you're going to multiply the minus c with these two expressions, okay, so when you're going to multiply the minus c with these two expressions, you're going to get what we call minus c times y plus a over 1 plus sigma square times minus c, which is going to be plus c times a square or sigma square. I mean, if you keep the value of the sigma c in your head actually, so it's going to be what? So it's going to be c times of it's going to be c times c, yani c is what? So it's 1 plus sigma square over 2 sigma square, 1 plus sigma square over 2 sigma square times a square over 1 plus sigma square actually. So a square over 1 plus sigma square square. Okay, so this will go away, and what you're going to remain is this actually, a square over 2 sigma square and 1 plus sigma square. So you're going to get minus c times of y plus a over 1 plus sigma square chi square plus, what do you call, a square over 2 sigma square and 1 plus sigma square. This is what that you're going to get actually. Okay? So, what do I mean by that? Now what I am saying, this entire expression is equal to, what do you call this? So, in the integral of exponential of this integral, I am replacing on the place of this expression. Okay? And keep in view, okay, so what you're going to get? Hence your let's call this equation star, this star or this integral will become hence star will become, okay, I know I'm doing messy calculations, but you know, we have to learn it, we have to do it, okay, so we have to learn to do such things, okay. So e to the a square over 2 sigma square 2 pi sigma, e to the